Just like the integral of the array.
Okay, we'll get started. Sorry to interrupt your conversation. But we'll get started. So, today the topic for discussion is practical RL. One small note that I wanted to make sure you guys make the change in the note. So, the pi f of a function h is argmin. So in some of the lectures, I seem to be missing this arg component. I've just written minimum. But make sure that you change your notes to argmin and not min. So in the previous class it was correct, but in lecture 19 I think it was wrong. So please make that correction. Okay, so today there is going to be very little theory. Whatever algorithms I'll talk about, there is no understanding of why it works, but it works very well for the specific problems that the authors are trying to solve. And so these are all the algorithms that were developed largely from DeepMind between 2014 to 2017 era. Okay, so anybody knows what the goal of DeepMind is? DeepMind as a company? No? So DeepMind started because they wanted to create artificial general intelligence, and so the idea was that they can train one super model, and that super model can do everything in life. Okay, that was their goal. That's how they started back in 2011 or maybe 2010, and then they got acquired by Google at some point of time. And so a lot of the work that came out of the practical methods in RL, it was largely coming out of DeepMind and people associated with DeepMind at that point of time. Many of them were faculty at UC Berkeley and Stanford. So a bunch of algorithms came out of it, some of which we have already studied, which is PPO, TRPO, and so on. S, soft actor critic. So those were some of the algorithms that came out of that research, and then the rest of the algorithms I'm going to be talking about today. Okay, so the goal was, so this is still the stated goal of DeepMind: create AGI. And how does that apply in our setting? So this is train mu theta that can accomplish a lot of activities. By the way, this is still one of the things that people are trying. So they want to train a neural network, train a large language model that can accomplish a lot of different activities, whether it's writing code, summarizing, giving you recipes of whatever food you want to cook, and so on. So a single transformer network that is able to accomplish a lot of activities. And more recently, in the last 1 or 2 years, the craze in the Silicon Valley is to create one vision language action model, so that you can tell the robot, okay, go and clean the board, and the robot is able to figure out where the board is and clean the entire board. So that's still something that people are working on. And the whole idea there is to train one single policy that can do everything or a large number of things. And then they call it AGI, artificial general intelligence, whatever, doesn't matter. So what DeepMind was interested in this particular era was, my state space S is an image / video of a game, and my action A is set of all images / video of a game, and action set is set of all moves in the game. And their goal was to create one single policy that can train a whole bunch of games, that can play chess, that can play Go, that can play whatever, 5 Atari games and so on. And that's what they wanted to figure out, like, how do I train a single model to be able to play a whole bunch of video games or a whole bunch of alternating move games like Go and chess. And so the key idea there was the policy gradient theorem that we have talked about. Which basically says gradient of theta, j mu theta, can be written as expected value of SA distributed according to C mu theta, and this is also the same thing as expected value. I'm going to introduce this C mu theta in a bit. And C mu theta of S in is S in B1, A in B2 is 1 minus alpha summation t goes from 0 to infinity, alpha raised to t, probability ST is in B1, AP is in B2, given S0 is distributed according to rho and AK is distributed according to mu theta. There is this 1 minus alpha term here because we want to make it a probability distribution. So I think there should be I probably need to divide it by 1 minus alpha here in order to make sure that the notations are consistent. So typically you don't have to have it as a probability measure. You can have any arbitrary measure, but I know that many of you here are comfortable with probability measures, so I'll do this normalization thing. This is something we have studied. It's called discounted state action visitation frequency. So this is something we talked about during the policy gradient lecture that when we were discussing. Yeah.
Just a quick question.
Yeah.
The nebula is with respect to a logarithm only, does not include Q or A.
No. This, yeah, perfect. Yeah. This is only the logarithm, not the Q. Q stands outside of this gradient. This is, by the way, this is something that you prove in assignment 4. Question 3, I think. So this is something that you have already seen and you have already proven. And I'm just using the result from the assignment. Any questions so far? One comment that I want to make here is that in this particular case, in the case of DeepMind, most of the moves in the game, the action set was all finite. You can either go left, right, up, down, something like that. So the set of moves were all finite in the many of the DeepMind papers that I'm going to talk about, but the state space was actually a general state space because the state space was usually of this form: 3 cross 19 cross 19, or 3 is for RGB, and then you could have 100 cross 100 depending on what kind of paper you are reading and what kind of topics you are talking about. And sometimes if you have a video, then you also have a time component, capital T here. So they look at successive frames of the video and then they extract some features out of it. And that's what they are using as the state space. In the case of robots / autonomous vehicles and so on, this still remains the state space of the system. So you're looking at the video of the autonomous vehicle, you're looking at things that are happening around you, and then you are constructing some sort of state representation of what's happening around you. So DeepMind's idea was to use the images or videos directly without any feature engineering. I think that it leads to a lot of sample complexity, like the sample complexity of the problem becomes extremely high. You need large number of samples to be able to train. So I think the idea of extracting features from very large state space is kind of coming back because you don't really have that much data to be able to train in the rich setting of autonomous driving and so on. Okay. One thing that I will mention is prior to 2014 or maybe 2012, the general understanding in reinforcement learning community was that this problem is extremely difficult. And the reason why it's difficult was because from 1990 to 2010, a lot of people, especially people who were working in the practical side of RL, they wanted to use neural networks to train mu theta and to train the value function or the advantage function or the Q function. And many of those investigations didn't really succeed. And of course, it wasn't very clear why they were not succeeding. So people came up with all kinds of theories. And we talked about inherent Bellman error, and inherent Bellman error was another theory proposed as to understand why certain reinforcement learning problems succeed versus why they don't succeed. So there were a lot of stuff that people were studying prior to 2014 in order to make it work, and they were not successful. And the key reason why DeepMind folks were successful is because they used completely different techniques in order to ensure convergence of the Q function and ensure convergence of the policy, and demonstrate that the policy is actually doing extremely well in the settings that they were interested in. Now, let me try to connect what DeepMind did. I mean, many researchers in DeepMind did, so it's not like one person, but a lot of people in DeepMind did. And what we have studied so far, right? So we talked about the projection, and we talked about pi hat of f. So we want to project. We can't really evaluate this particular function, this error. So I'm going to use some samples in order to approximate the error, in order to do the function approximation part. So remember that in pi hat f, I had said that you need to sample the states, or you need to sample the state action pair depending on whether you are projecting a Q function versus a value function. The question really becomes, how do you sample the states? What's the way to sample the states? What's the measure under which you are sampling the state? And I want you to think about these large state spaces. Okay? We ourselves have worked with state spaces that are of the order of 1 million. So integers raised to 1 million. Okay, so that's roughly the state space that we have trained things on. So now you are in such a high dimensional state space. How are you going to sample? What sampling method would you use in order to do this projection? Okay, that's the first problem. So question 1, how to sample SIAI 1 to n for the projection operation. Question 2 is, what NN architectures work? What should be the loss function slash update scheme for neural network? And there are 3 approaches that will cover our entire lecture today. The first approach is that we'll talk about is experience buffer. Second is Tmax step rollout. Third one is reward shaping. Using a potential function. Is everyone here familiar with the support of a distribution? What is the support of a distribution? Do you guys know? Okay. So the support of a distribution, let me use C, is intersection of C as a subset of S cross A. C is closed. And CC is equal to 1. So what's the smallest closed set where the distribution, the measure is equal to 1? That's called the support of a distribution. So this is the smallest set where the probability of that entire set is equal to 1. Okay, that's called the support of a set. And generally speaking, support is closed. Okay. I'm not quite sure why it should be closed, but for whatever reason, people, whenever they define support, they define it as an intersection of closed sets. Okay, so this is the smallest set where the probability is 1. Now let's go back to Uber example. So this is day 100 of Uber. You've collected a lot of data in Uber and you have a very bad policy today. And under the bad policy, what's going to happen to the customers? What's going to happen to the drivers? Okay. So policy there is you want to match the drivers to the riders, and you have a very bad policy. So under bad policy, most riders are going to see a very high waiting time, and most drivers are going to see a very high empty vehicle miles traveled. Okay. So in some sense, you are visiting the bad part of the state space very often under a bad policy. Okay. So if you look at a bad policy, let's say mu bad, and you look at the support, let me draw a diagram. So this is my state cross action set. And I'm looking at the support under a bad policy, and it's going to look something like this. This is my support of C mu bad, and this is my support of C mu good. So for a good policy, you are going to be visiting states where the waiting time of the passengers are low and the empty vehicle miles traveled by drivers are low. Under the bad policy, the waiting times are high and the drivers are driving long distances without passengers. If you have a bad policy, the only states you are visiting, state action pairs that you are visiting, is this region. But ideally, whatever Q function you are training or the value function you are training in order to get to the optimal solution should be trained here, right? But you don't even know in a million-dimensional state space or a 1,000-dimensional state space, you don't even know where this part lies, okay? And that's one of the critical challenges of reinforcement learning. As you are changing the policy, you want to actually move from this particular set to this particular set. So if there is a set mismatch and you are trying to train a function here and you want it to perform very well here, what is that called? That phenomena is known as generalization in the machine learning literature. So I'm sure all of you might have heard about the term generalization. What is generalization? I have trained a function on this set. I want that function to do well here. Okay. In very high dimensional reinforcement learning problem, you generally don't have, these two sets are very far apart, as a result of which whenever you train something here, you will have very poor performance here. So what do you do in those situations? What can you do? So you have a bad policy today. You want to get to the good policies in the future, tomorrow. How can you go from bad to good policy without necessarily exploring the good states? You don't even know what the good states are in this high dimensional state space. Anyone knows what are the good chessboard configurations are, which is advantageous to you but not advantageous to the other person? Probably no, right? We can't really construct, we don't even have an idea of what all board configurations would be advantageous to us. So the way you solve this problem is every time you update the policy, you generate a new set of data. Okay. Now, if you do a single run of your policy, so you collect this, you're collecting this data, but you're collecting it along the single trajectory. So you start with S0, you go to S1, S2, S3, S4, you collect all the rewards or all the costs. So by the way, today I'm going to talk about rewards because DeepMind writes papers with rewards. So what happens in those situations is you are essentially looking at a specific low dimensional manifold of this set. Okay, so you start from some initial state and you are generating data and trajectory, and you're not even observing the entire set. All you are doing is going along a certain line within this very high dimensional set. So you are exploring, even though you are collecting data from one stream, you are actually getting data from a very small subset of this set. Okay. More importantly, if you train your data using just the data from this particular line, you won't really generalize well here, you won't generalize well here, you won't generalize well here. Okay? So what do you do? So I did one run, I collected the data, the state action pairs along this particular line. But I guess the point is that I shouldn't really train my function based on the data set that I've collected in one run. I should be collecting multiple runs of the data, right? By collecting multiple runs of the data, now I have covered a lot more area of the state space. Then what do? The problem is that if you use one of these runs to train the Q function or to train the value function, you have a lot of correlated samples, and those correlations would derail, will have bad generalization error if you're using that to do the function projection. So the idea of experience buffer was to collect all of this data in a buffer, in a very large buffer, and then sample independently from those buffers. That's called the experience buffer.
Can't we do some feature engineering to exploit the correlation?
The idea of DeepMind is not to do feature engineering at all. That's their corporate goal, corporate mandate. Do not do any feature engineering. Image in, policy out. That's their goal. It's coming back though. Now people are doing feature engineering because that's what you have to do in high dimensional systems, but that's not what they wanted to do. Okay, so what is experience buffer? So this is, I'm going to collect data SI, AI, RI, SI prime. So SI prime is the next state that you, so SI is the current state, AI is the action that you have picked, RI is the reward that you got, and then SI prime is the next state that you visited. I equals 1 to n. Typically this n is extremely large. But there is a small difference here. So you're not doing a single run, you're doing multiple runs, and you're collecting all of that tuple, 4 tuple within your data set. And in fact, you are filling it up even with older policies. So experience buffer, this contains data from the current policy. So mu theta k, mu theta k minus 1, mu theta k minus 2. So this is experience buffer at time k, and so on, k minus delta. So you're not stopping it at delta. As your new experience is coming in, you are pushing it into the buffer, and whatever old experiences you have accumulated, you are pushing it out of the buffer. Yeah.
Is this the same as the replay buffer that we have?
Yes, yes, yes. Okay. So now you have, you have not just computed. So this is support of mu theta k minus delta. This is the support of mu theta k minus delta plus 1. This is the support of and if you have a whole bunch of trajectories that you have sampled from each of these buffers. And what you are doing is, as you are collecting new data, you are removing old data from the buffer. And so now you have data set from a very big area of the state action pairs that you have visited. and then you sample IID from this particular buffer in order to do the projection operation. You're sampling IID from this buffer and then doing the projection. And that way, you remove all the, arguably you remove all the correlations between different samples, as a result of which you have much better generalization performance, because now you're looking at a very wide range of the state action pairs that are visited under the currently known optimal policy and the previously known optimal policies. Okay, up to a certain limit, because the experience buffer is still limited. So as new data arrives, old data gets removed. So there is no fixed delta here. It's just that whatever data is coming, you're pushing out all the previous data, and as a result of which there is some truncation that is happening, after which you're not collecting the data. So as you are moving from here to this particular location, you're collecting data set in the intermediate parts of the state space, and you're training your Q function or the value function at all of these locations within the state space. That's the idea of experience buffer. Yeah.
Still doesn't seem to be enough to me, because the high-dimensional space is so large.
Yes.
Why are we moving in the right direction? Why are we not moving in some, the right direction is one of many, many directions.
Right.
So it's not clear that we wouldn't move opposite of a good direction.
Very good point. The way you compute mu theta k would be arg max. So remember, we are in the reward setting, so I'm doing arg max A in AS Q theta k SA. So you're always improving on the current estimate of the Q function. Actually, I should write it as mu theta k minus 1. So you're always moving, you're always optimizing the Q function. Now, assuming your Q function set, the set of neural networks that are approximating the Q function is sufficiently large that it can fit all kinds of continuous functions, from state actions to the real numbers, this one would be optimal.
Chicken and egg problem. And we talked about this earlier. Maybe it was in the context of the multi-arm bandit, where if you train on data that doesn't include the optimal data, then you're not necessarily training the right. You're not minimizing the right, maximizing the right reward. So here, again, it's not obvious to me. If I really knew the objective, then yes, I would understand that we would improve it. But if I don't actually know the objective, if I'm trying to approximate it with bad data,
yes,
why is that going to generalize? Because you said earlier,
yes,
it might not generalize.
That's right.
Saying it will generalize.
That's right. I mean, these are all hand-wavy arguments. It works, and when it fails catastrophically, and nobody knows why it's failing. But when it works beautifully, and it defeats the best chess grandmaster in the world. And so DeepMind's point of view is, we'll train this and we'll defeat the world champion. And they've done it for chess, they've done it for all kinds of games. And this is the algorithm that seems to be working out well for them.
Previously, you talked about other tricks.
There
was some kind, I forget the name, some kind of regularization that, bias, I think it was, the word bias was in there. It was some extra term that biases us toward.
Oh yeah, the in the multi-arm bandit setting. Yes.
That was the critical piece.
In the multi-arm bandit setting, yeah.
This being stuck with bad data.
Right. That's right.
Data.
That's right.
You're saying you don't need that here? Reward bias.
Right. So yes, reward bias. Okay. So you don't. So each of these policies that are constructed is the argmax, and then there is also the exploration term. And the exploration term is typically epsilon greedy, or it could be some other forms of exploration. So I'll talk about exploration in a bit in the general state space setting. In the case of DeepMind, they are generally using epsilon greedy, or they are using some form of Boltzmann exploration. Okay. They don't call it Boltzmann exploration, they call it some temperature term, and it's some way of doing exploration which is somewhat complicated to describe on the board. but certainly you can go back to the papers and figure out how they are doing the exploration. So there is mu theta is constructed by doing argmax and plus some exploration term. There is one case for the continuous case where I'll explicitly mention what the exploration term is, but here the exploration terms are somewhat complicated. And depending on which paper you read from DeepMind, they'll have different exploration techniques for making sure that you are covering some part of the support.
So this procedure may have the risk of ending in a local optimum instead of a global one, I guess.
True.
Yes,
all
that's
deep
the
learning.
case with all of deep learning.
As long as it's a good enough.
Yeah.
And then,
See, if you can defeat the world champion and you get the press coverage, that's good enough. Even if it is local minimum, how does it matter? Okay. Okay, so that's the experience buffer. Is the idea of experience buffer clear? So you're moving the support, you're trying to sample from a large enough support, and the support that is slowly drifting towards the optimal support where you will have the maximum reward. And this is all empirical in nature, so I can't comment on the theoretical side of things. Yeah.
When you sample from your experience buffer, if you're sampling from supports or I guess data sets generated with an older policy,
That's right.
The most recent one,
Yes.
do you have to do important sampling, or do you have to do the?
You don't have to do any important sampling. No. So there's no important sampling here because you have this state action reward and the next state, and you have the current estimate of the Q function. And you want to get the next estimate of the Q function, you use the current estimate to estimate the next Q function. Okay, so I'll talk about it in a bit. Right now, I just want to cover these three different distinct topics, and then I'll talk about how the policies get updated at every point of time. Any other question? Okay. So everybody is clear about experience buffer. I'll talk about T-step rollout.
are these techniques alternatives? Are they like mutually exclusive, or are they just together?
It's mix and match. So there are different algorithms which will mix and match different techniques in order to make things work. Okay, so now I have this. I have the current Q function. Let me call it Qk of SA, or k minus 1. This is my current Q function estimate. So there is some neural network that is parameterizing this Q function. There is a convolutional neural network. There is an RKHS or whatever that's parameterizing the current Q function. And I'm collecting this SI, AI, RI, SI prime, I equals 1 to capital N. I've collected this set from the current policy, previous policy, whatever. I've done some actually, in this case, I need to be explicit about the time index as well. So let me use SI T, 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 and this is generally SI T plus 1. So I have n different places, and then I am going to go from T equals 1 to, or T equals 0 to T max. So the idea in n-step rollout is the following. I'm going to define my YIT to be equal to RIT plus alpha times RIT plus 1, alpha square times RIT plus 2, and then so this is known as a rollout, and you're using multiple step rollout in order to compute the value of aggregate reward. So reward, discounted reward at the next time step, discounted reward at the next time step, all the way up to T max minus T. And then you put the current estimate of the Q function at the end of this rollout process. And then you define your Qk of SA, not SA, but Qk would be argmax, argmin of function class G and summation I equals 1 to n, summation t equals 1 to t max So you do the function fitting in this particular manner. G is your function class for approximating Q function. So remember, when we were talking about this one-step rollout, we used to consider the Q function at multiple states. We'll take the sample average, and the T max will be just 1. So I'm just looking at the next state of the next time of the Q function. So now in the T max step rollout, you are trying to roll out this thing for multiple time steps, and then you are aggregating all of that data in this new variable yi of t, which you are using for doing the function projection. So so in general setting, T max was equal to 1. So you didn't have to have this inner summation. You just pick some state action pairs and then you do this function approximation. Now you are being you're looking at a longer horizon and you are doing this function approximation using this longer horizon data. Okay, so this is known as a T max step rollout. And this was another thing that has improved performance dramatically in the reinforcement learning setting. One of the recent papers suggested that this is the most important reason why reinforcement learning works. But they don't have a proof, they have an empirical investigation, and they say that this allows you to improve the performance of reinforcement learning over all other things that people have done in the past. I've read the paper. I'm not sure if I 100% agree with the conclusion. Okay. That's the next idea. Any questions on this? Yes.
So for this Tmax step rollout approach, it's used typically in actor predict for the critical.
Exactly. Yeah. So A3C algorithm is something that hopefully I'll get time to cover today. That's what promoted this Tmax step rollout idea in the RL setting. I mean, it was there earlier also, but they actually made it work in the neural network setting, and therefore that paper has again a lot of citations. Okay. So this one is anybody has any questions there? No? Now you can do other things as well. You can do batch sampling, like this data set is extremely large, so then you can take IID buffer and you can do batch sampling and you can do this, solve this problem by stochastic gradient descent of some sort. So you can do all of that because your T max and n could be extremely large, and therefore you might need to use stochastic gradient descent to solve this problem. So that's roughly what people do. And in one of the papers that I'll talk about, not only they did stochastic gradient descent for this, but they also applied momentum method. So they did stochastic gradient descent plus momentum method in order to solve this problem. Anyways, so that's the rollout. The third one is reward shaping, and this comes from a paper in 1999. Can I raise this slide? Okay. So there is this is reward shaping. This is so the idea is as follows: you pick a potential function. You have a reward function, define a new reward function S A S prime to be the old reward function plus alpha times P of S prime minus P of S. I'll use small r. So you add alpha times the potential function at the next state minus the current state. And their theorem in the paper, this was proved in a finite state, finite action setting. So I don't know whether it works in the general state setting or not. But people have talked about using it in the general setting as well in one of the papers. The theorem is that optimal policy for R is the same as optimal policy with R tilde. So if I pick the optimal policy with the reward function R, I have the same MDP, I just change the reward function with R tilde, I get the same optimal policy. So there is a correspondence between the optimal policy for this reward and optimal policy for this R tilde. Now let me tell you why this reward shaping works. The idea in reward shaping is that suppose you are solving a problem where you get the reward at the end of the horizon. So bulk of the reward is at the end of the horizon because you won the game or you reached a terminal state that you wanted to reach. You wanted to go from home to office, and so you reach the office, and that's the terminal reward that you get. So the bulk of the reward is at the end. And the problem that people had observed before 1999 is if the bulk of the reward is at the end of the horizon, then doing reinforcement learning takes a long time, extremely long time. And many a times the reinforcement learning is not successful in learning the policy. So then the question was, how can I give more intermediate reward for the agent to be able to learn how to get to the end goal state? So they came up with this idea of potential function and said that if you add this, if you have a potential function, typically you can pick phi of S to be some difference of some distance from the goal state. So that's one way to define a potential function. So that way, every time you are going towards the goal, you are getting a better reward, and every time you're going away from the goal, you're getting a poor reward. And that's how they are. What they say is that you sort of do the reward shaping, as a result of which you can learn much faster. And they showed in their paper empirically with very small, somewhat small state space, because this is 1999 paper, so they didn't do very complicated studies, but for reasonable size MDPs, they showed that this reward shaping learns the optimal policy extremely quickly. Okay, so that was the breakthrough in that particular era.
Do they have access to X goal?
Do they have access to
S goal?
They do have access to X goal. Like you know at what point of time you are going to get to from point A to point B. So what the problem that they were more interested in is riding a bicycle to a goal state. How do you start from this state and then get to the goal state? And so in robotic setting, this is extremely easy and straightforward because you know what the goal state should be. I want to go from here to there. That's my goal state or goal configuration of the robot. So they do know this, and in which case the reward shaping. So this theorem is more general, not just for robotics, but the problem they were interested in is robotics problem. And this idea of reward shaping has, it has a lot of citations, I think 7,000 or so citations, but I've not really seen a success story with reward shaping outside of some limited papers that I've read. But that's because I myself have not read those 6,000 papers. I'm sure it's important, but because I have not read them, I don't know whether it has done well or not. Yes?
Seems like we need to change the sign somewhere because, right? Because this is a penalty on getting to the goal, whereas you actually are interested in the reward. So like when you're far from the goal,
Right.
Phi is large, which increases your R tilde, it seems.
When you are far from the goal,
Then Phi is large, Phi of S is large.
phi of S is large.
Oh, I guess, yeah, because there's these
This
two
one is
terms,
small.
there's like the current state and the next state. And they have
This-
opposite signs.
Let me think.
Last term from this or the first term from this?
So this is a cost, right? So this is a cost that you are subtracting from the reward. So you're far away and you want to get closer.
Oh, it means the last term is.
Yes.
What's the like norm definition of the
Potential function.
That's telling you that if you're moving farther away from the goal, your reward is increasing.
So if you are moving farther away from the goal, then phi of S is very large.
Yeah. So if S prime is farther away from the goal than S, then your reward is increasing.
Oh, I see. Okay, let me think. Okay, so if I put a negative sign, then what happens? So now my reward is high, and if I get closer to the goal, then I'm not getting enough reward, right? This one is the discount factor.
Yeah.
So let's assume that the discount factor is very small, 0.1. Or let's say it's 0.9. Then what happens? Let me check on this and I'll get back to you. I'll read the paper and figure out what is the potential function they are using. But it could be either plus of S minus S goal or negative of S minus S goal. I'll have to go and check. I don't have the printout with me of that particular paper right now. Yes.
Does the theorem hold when the phi is required to have some structure?
Phi could be arbitrary function. Remember, they are doing it for the finite state setting. They're proving the theorem for the finite state setting, so the phi could be any function. Now, certainly some potential functions are better than the others. So you want to ideally pick the potential function that works best for your specific problem. Yeah. Yes.
So it seems like in a lot of cases there's many goals. Like if you think about chess, there's many ways to win a chess.
That's right.
Many
Yeah.
states you want to
Yes.
win.
Yes.
So if I have like multiple states and in some high dimensional space they're orthogonal,
Right.
do I have like this how do I handle that?
I don't think anybody has thought about it.
Okay.
But I have not seen the papers, like I said, this one has a lot of citations. I have only seen 2 or 3 papers you citing this particular paper. Maybe somebody has looked into it. I just may not be aware of it. Any other question? Okay, so the idea here is to use the potential function which is tied to the goal state that you want to reach. And largely speaking, the people in 1999, they were more interested in making a bicycle go to a goal state, and that was the main issue that people were interested in solving. Okay, so I think 3 different ideas that people have tried within the reinforcement learning community, and they have gotten pretty good results. Now let's talk about specific papers that tells you that uses these 3 ideas in order to and then I'm going to talk about how exactly they are updating the neural network, because that's okay. So the first paper I want to talk about is deep Q network paper. So the title is Human Level Control through Deep RL, and this algorithm is generally referred to as DQN, Deep Q network. So here the key feature is one-step rollout. Policy gradient. Computation using IID samples from experience buffer. Okay, so this was the first paper that talked about experience buffer and doing IID samples from the experience buffer in order to update the Q function. And they are using only one-step rollout, so they're not doing T-step rollout. So one-step rollout, which is the typical way of updating the Q function. And remember, in the previous lecture, we were talking about, in order to get a reasonable estimate, reasonable projection, you need to use n samples of the state action pair in order to do the projection. Here, n is equal to 1 because they pick one sample of S, A, S prime, R prime, R, and then they use that for the computation of the policy gradient. So in other words, their loss function Qk plus 1 equals to argmin of Q in the function class G, summation I equals 1 to n, Ri plus alpha max of Qs Si prime A prime. This is how they are doing there, QK. Q. This is how they are doing the projection of the Q function. So we had in our previous lecture, we had summation of I equals 1 to n. So we were taking n samples of this and then we were doing projection. But here they are using only one sample of the next state in order to do this. And it works because this was one of the first papers that showed that you can play complicated games using deep reinforcement learning. This one was solving, so the state space was images of 210 cross 160 pixel and 128 color palette. And this is from Atari 2600 games. Okay, that's the state space that they are talking about in their paper. One important note here is that they are only interested in computing the Q function, and then after they have figured out what the optimal Q function is, they figure out the policy by doing this argmax of the Q function. The other thing that they said they did was the input to the neural network is the state. The output is Q of SA1, Q of SA2, Q of SA3, and so on. So they have like 15 or so actions in their problem statement. So the output of the one part, so at the final layer of the neural network, it is outputting the Q function in each of those n different actions. So it was a finite set of actions and they were directly outputting the Q function. The great thing about this particular architecture is that you can figure out what the best action is just by looking at what the highest Q function is within this set of possible outputs of this particular neural network. And then they also used, at every point of time to collect new samples, they used epsilon greedy with epsilon equals to 0.05. So you have simulated epsilon greedy algorithm in your assignment. So they are using that epsilon greedy exploration strategy while generating the data set. I think this paper has maybe 40 or 50,000 citations or something like that. So it was one of the early papers that said that deep reinforcement learning can be very successful in complicated situations. That was the main idea in this particular paper. Any question on this? Okay. Let's look at the second algorithm, which is DDPG. Deep deterministic policy gradient. This was 2016 paper. So here I am going to change the exploration policy. It's also one-step rollout. So no multi-step rollouts yet. Policy gradient computation using IID samples from experience buffer. So that also remains here. The exploration policy is slightly different. And they have two separate networks. So mu theta and q. So one is the policy network, mu as a function of theta. They call it theta q, but then there is double q appearing here. So, okay, let me use their same notation that they are using rather than our notation here. So that makes it clear. So they have mu s theta mu and q s a theta q. So they have two separate networks. So they are not using a single network. This one had a single network. This one doesn't. The S is S and A are subsets of Rn. So this is done mostly for the robotics sort of areas, so continuous control. This one was discrete control, as I mentioned, because the action sets, the number of possible moves you have in a game is finite, so you can have it in that manner. This one has continuum of actions because actions is a subset of Rn. So you have to use a policy network in order to tell you for every state what the action should look like, and then the corresponding Q function, which takes as input state and action and evaluates what the Q value should look like. They had a very interesting exploration scheme. Which they have not written it completely. They said that they used OU process to develop the exploration scheme. So I'm going to write the discretized version of what they have written in English. I'm not sure whether I'm right or wrong, but take it with a grain of salt. So they define nt plus 1 equals to minus 0.15. So delta t here is the time difference between t and t plus 1. So whatever is the 1 unit of time, that's delta t here. So you can substitute that. And this is Gaussian 0, 1. And then the policy for exploration. So the data collection policy is so the action is whatever the current policy is plus this noise that is evaluated in this particular process. So this is known as discretized OU process. So this is how they are doing the exploration. So this doesn't fit into all the exploration that we have studied in the class, but this is what they have used in order to come up with the data set in order to train the Q function.
What is the delta t?
Sorry?
What is the delta t?
Delta t is, so remember in a continuous time setting, going from t to t plus 1 will be something, right? 100 millisecond, 500 millisecond, 1 second or whatever. So you put that delta t here. So if it is 100 milliseconds, this will be 0.1. If it is 1 second, then delta t will be equal to 1 and so on. Okay. Yes.
Is there any rhyme or reason to like the 0.15 and the 0.2, or is that just
No, that's just what they have written in the paper. So I have just written that down from their paper. Generally speaking, what happens is a graduate student would run multiple simulations with multiple values here and here, and whatever works best, that gets published. Everything else gets not published. Okay, and then they have a very So after doing the data set, after collecting the data, after doing this one-step rollout, once they compute the gradient, then they update the gradient in this fashion. Theta q is tau, which is the step size. Theta q k plus 1, theta q k plus 1 minus tau. So after you compute the gradient of the policy function as well as of the Q function, you use this particular update scheme. So this is the gradient. And now you are not doing the entire update. So remember here, when we do this argmin, we are actually computing the new set of values, new set of parameters. Here what they are doing is once they compute the gradient of the new parameters for the neural network, they're not replacing the new value with the old value. They are using some sort of learning rate in order to update the Q, the parameters for the Q function and the parameters for the policy. And the reason that they mention in their paper is it makes things more stable. So if you keep changing the policy, if you keep changing the Q function according to this fashion, in the continuous control, so you're completely replacing the weights with the new weights, it turns out that there is a lot of instability, as a result of which they are sort of not changing the weight very rapidly. Yes?
The gradient is computed at 2K and 3K.
Yeah, that's right, that's right. Yes, you're right. They also use experience buffer, and they also use policy gradient for and this Q function for computing this gradients with a specific exploration scheme. Okay, then we have advantage actor critic. The only way they differ is multifold. So asynchronous advantage actor critic. Let me write it here. So they came up with this, or rather they used Tmax step rollout. That was the key feature in their paper. They call it A3C algorithm. And in A3C algorithm, they use this Tmax step rollout, and then they update the gradients using stochastic gradient descent. The other thing that they had was, instead of running one simulation on one CPU, they had n simulations running on n CPUs, and then they were collecting the data and computing the gradient and so on. So that's the asynchronous part of the advantage actor critic. So advantage actor critic is you have one CPU, you have one simulation environment, you're collecting data from one simulation environment. Asynchronous advantage actor critic is you have 20 CPUs, you have 20 different versions of simulators running, you're collecting data from 20 different CPUs and then using that for gradient updates. And the idea again there is to remove the correlations across samples. So in the experience buffer, you now have samples from 20 different experiences of 20 different simulators of the same system. So it's not like simulators are simulating different systems, but you have the same system, you're simulating 20 different on 20 different CPUs. So therefore now you have uncorrelated samples, and you can use IID data from the experience buffer in order to update the gradients of the Q function and the value function. Okay, do I have time? I have 5 minutes. So I'll talk about our own paper and why there was a completely different way of computing the state and action pairs in those in our paper. So let me give you the idea. So in our case, we knew what the model is. It's just that the model was extremely large. So we were solving problems where state was R1000, the action space was R200, and we had state dependent action set. We had A of S specified. We knew W, we knew F, and we knew the noise distribution. Okay, so we knew everything about the system. It's just that because it was a very high dimensional problem, we needed to run the empirical fitted value iteration algorithm because we can't do the true value iteration in this case. And we also face the same issue as to what are the states that we should be using for projecting. Okay. So here is the idea that we came up with, or my graduate student came up with, which turned out extremely well for our specific setting. We solved the following problem. We were minimizing the cost. So we had a cost function. So I'm going to minimize t equals 1 to capital T, Ct C of STAT. I'm going to minimize it with respect to AT, t equals 1 to capital T, such that ST plus 1 and AT is in A of ST. And then WTI, I equals 1 to capital T, sampled IID from N. So remember, my goal here was to sample from the good part of the state space, not from the bad part of the state space. Remember, going back to our first initial discussion. The question is, I don't know what the good part of the state space in this high dimensional state and action space looks like. So how do I know what the good part of the state space is? Well, I'm going to generate the samples, noise samples, according to the distribution that I know already. And I'm going to let the simulation run for t time steps. And I'm going to minimize. Now this becomes a deterministic problem. It's no longer a stochastic problem. And I can figure out what the optimal actions are, and I can figure out what the optimal states are for each of the set of noise samples that I've generated. Now I have some notion of what the optimal states are going to look like in the what the optimal states are going to, so what the optimal states region in the state space is going to look like. And in our case, these states were used, whatever states we figured out what the optimal states were at A star of t at these noise samples, we used those states to do the function fitting. It worked beautifully. And the reason I think it worked beautifully was because our variance in the noise was very small. Okay. So if the variance is small, and you solve this problem, you pretty much get the states in the good part of the state space and not the bad part of the state space. So in theory, I would have needed a lot of different samples from the entire state space, but in practice, we didn't have that much computational power. So this is the way we generated the state, and it worked really well. And Ford has filed a patent for this theory, not the theory, but the algorithm that we had developed. So they are probably going to use it for their EV charging system at some point of time in the future. I don't know when. But this is something we did for Ford Motor Company. Yeah, go ahead, please.
Oh, so the target here is undiscounted finite horizon, right? The objective.
That's right. In our case, it was undiscounted finite horizon problem, but I think you can do it for infinite horizon as well. It's not going to be too different as long as this t is appropriately pegged. So remember that so you have alpha raised to capital T, right? So you have alpha raised to T. So you don't care about the states that come far in the decision process. You care about the intermediate states from S0 to a certain time step where alpha raised to T is very high. And so this is the way, one potential way of identifying what the good part of the state space looks like. Yes.
Is the minimization with like stochastic gradient descent?
Actually, in our case, this was a linear function, this was a linear function, this was a linear constraint. So we could just do linear programming to do it. If we didn't have linear functions, then it could have been much more complicated. I don't know if we would have, what kind of thing we would have used, but you can also use Pontryagin minimum principle for solving this problem. We cover PMP in our ECE 5500. So those of you who have taken would know that algorithm. Any question? Okay, perfect. So as an action item, I have to figure out the potential function they have used in the paper. So I'll send out an email with the potential function. If there are any other questions, I think I have my office hours right after this class. So feel free to drop in my office hours. And next week on Tuesday, we are going to be discussing about generative AI and specifically reinforcement learning with human feedback. Thank you so much.